So we're in section 5.2. All right. So what we're going to do today is our lesson today. We have two theorems and their converses is all we're really talking about, and they all have to do with these perpendicular and angle bisectors. So the first one we will call the perpendicular bisector theorem. I'm not really worried about the name. We just want to call it something. So before we even write what the theorem is, let's talk about our words. Perpendicular. What do we mean when we say perpendicular? 90-degree angle. Perpendicular means it makes a 90-degree angle. Bisect means through something in a special way. Someone said it. What was it? In the middle. So the bisector goes through in the middle. What's a kind of everyday way that we think of going through the middle? What does it do to the other thing? Cuts it in half. Bisector cuts something in half. That's usually how I think of a bisector. So perpendicular bisector is something that cuts something in half at a 90-degree angle. So what we're going to say for our theorem is that today we have a lot of words today. Sometimes geometry has a lot of words. If a point is on the perpendicular bisector, of a segment, then it is equidistant. Equidistant means what? What do we mean when we say equidistant? Equal distance. Just two different words. Equidistance means equally distant. So it's the same distance from the endpoints of the segment. So let's draw a picture about what we're talking about here. So here is our segment, and here are our endpoints. And we're going to draw a perpendicular bisector and make it a line here. So there's our perpendicular bisector. So it makes a 90-degree angle. That's what the little corner means. And those two are congruent. Cuts this segment in half at a 90-degree angle. And we have a point on this perpendicular bisector. There's our point. Call it P. What this theorem says is that that point is equidistant from the endpoints of the segment. So if we have a point anywhere where we are on this perpendicular bisector, that point is going to be the same distance from the endpoints of the segment. And the way we write that in symbols is, so here's our picture. Symbols, we would say if, let me put some more, label some points here, P, M, A, and B. If line PM is perpendicular to segment AB, well, upside down T means perpendicular, and AM equals MB, so these two pieces are the same. Then PA equals PD. And these two pieces are the same. So anywhere we are along this perpendicular bisector, we're the same distance from the endpoints of the segment. So let's look at this picture really quickly and think about, say we didn't know that these two red segments, we didn't have this theorem yet. We didn't know that these two red segments were congruent. Well, what do we know? So we have these two triangles. What do we know about this middle piece of the two triangles? The mid segment would connect two sides. Think back to chapter 4. What do we know about this side that the two triangles share? If we wanted to show that these two, I left out a piece of information. If we're trying to show that these two triangles are congruent, what do we know about that segment? It's congruent to itself. So we have this side congruent. We know that these are 90-degree angles, so what kind of triangle do we have here? A side, angle, side. So we could show that those two triangles were congruent by side, angle, side, because we have this side, we have the 90-degree angle, and this side's congruent to itself. So the two triangles would be congruent by side, angle, side, and then these two sides would be congruent by CP, CTC. Corresponding parts of congruent triangles are congruent. So we could prove this theorem by showing that those two triangles were congruent. And that we start off doing that by saying that that middle piece is congruent to itself. You remember what we call that property, or something's congruent to itself? Reflexive. Very nice. All right, so there's our perpendicular bisector. This is going to let us figure out lots of interesting things about triangles and other shapes. Let's write the converse now. How do we make the converse of an if-then? We turn it around. We change the order. So we're going to write the converse, which turns out to be true also. If a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So this is saying that if we know that our point is equidistant from the endpoints of the segment, that guarantees us that we're on the perpendicular bisector of the segment. So to draw a picture of that one, we're just kind of going in the opposite order. So here's our, that's not what I wanted to do yet. Here's our point, P. And here we're starting off knowing that this point is equidistant from the endpoints of the segment. So now if we draw our perpendicular bisector, I'll draw it in red. That's what we're doing because we're doing it afterwards. So here we're going to draw it. There's our perpendicular bisector. So we draw in our perpendicular bisector, and this point is on that perpendicular bisector. So for this one we say it just goes in the opposite direction. If PA equals PB, then line PM is perpendicular to segment AB, and AM equals MB. So this perpendicular bisector, it gives us some interesting and powerful tools. Anytime we're on this perpendicular bisector, we're equidistant from the endpoints of the segment. Anytime we're equidistant from the endpoints of the segment, we know that that point is on the perpendicular bisector. So questions on the theorem? All right, let's look at an example of the type of problem that we might get that has to do with perpendicular bisectors. So here's our picture. Oops. We have this triangle. And this is perpendicular. These are congruent. And this side is 6x minus 1, and this is 3x plus 8. And our question is find MN. We want to find the length of segment MN. So let's take a look at what we know here. This segment's cut in half. MO cuts this segment in half, and it makes a 90-degree angle. So what kind of thing is segment MO? MO is the perpendicular bisector. Makes a 90-degree angle, cuts it in half. So what does that tell us about how point M is related to the endpoints of the segment? What do we know about these two distances now? They have to be equal. Point M is the same distance from each endpoint of this segment. So we know that MN equals MP. So I can say 6x minus 1 equals 3x plus 8. Those two segments are equal. So how are we going to solve this now? Should be on 3. What do we want to do first? Add 1, okay? So I get 6x equals 3x plus 9. Next step? Good. Subtract 3x. So 3x equals 9. Now we've got it. Divide by 3, and x equals 3. All right, we're done, right? No? No? We're not done. What do we have to do? Find MN. It doesn't say find x, it says find MN. So here's MN. So MN equals 6 times 3 minus 1. 3 times 6 is 18, minus 1 is 17. So there's our answer. MN is 17. Because this is the perpendicular bisector of the segment, we know that those two had to be equal. What kind of triangle do we call this kind of triangle? These two sides are equal. The lengths of those two sides. Isosceles. Two sides, two congruent sides. It's an isosceles triangle. and didn't we talk the first semester about the perpendicular bisector, or the bisector, angle bisector of an isosceles triangle cuts the base in half? We talked about that. So anyway, we have an isosceles triangle. And we know that because this was a perpendicular bisector. Questions there? All right. So now we're going to talk, same kind of thing about angle bisectors. We have one theorem that has to do with angle bisectors, and it tells us some other special things about angles and segments and sides of triangles and that kind of thing. All right. So this is going to be our angle bisector theorem. Some more words. Still section 5.2. We just have these two theorems in section 5.2. Angle bisector. So what's the angle bisector going to do to the angle? Cuts the angle in half. Angle bisector cuts an angle in half. So we're going to say if a point is on the angle bisector, of an angle, it is equidistant from the sides of the angle. So if we think about what this is telling us, if we cut an angle in half with a line or a segment, it's saying that segment is basically halfway between the sides of the angles. It's in the middle of the angle. Well, that kind of makes sense, right? We're bisecting the angle, we're cutting it in half. So whatever's cutting it in half has to be right in the middle, right between the two sides. Now before we draw a picture here, I want to back up here really quick. I'm going to add another page here. Really quickly, how do we find the distance from one thing to another? So distance formula. So that's correct. Let me refine the question a little more. If I wanted to walk over to the wall across the hallway, what direction would I want to walk compared to that wall? How would I want it if I wanted to travel the shortest distance? Straightest path, right? I don't want to. If I want to go the shortest distance, I don't want to walk clear down by Mr. Evans' room. I want to walk the straightest path. So the straightest path, if I walk the straightest path towards that wall, how would I say that with math words? The shortest path, the straightest path, the direct path. What angle would I be making with the wall if I was walking directly towards it? 90 degrees. So the shortest distance from a point to a line, to a plane, whatever, we're going to make a 90-degree angle. So just kind of a reminder here, I guess. It's an idea that we all kind of have in the back of our head. I just want to make it more clear because we have to talk about the distance from a point to the side of the angle. So the distance from a point to a line is the perpendicular segment to the line. So that's what we mean by walking directly towards it, going straight towards it, going on the shortest path. That's going to be our shortest distance. So if I draw a picture here, if we have a line and I have a point, out here, and I want to figure out the distance to the line, we're going to the line at a 90-degree angle. And this is the shortest distance. So when we go the shortest distance, we make a 90-degree angle to the line. That's what I wanted to remind you of. Okay, so now we're ready to draw our picture. So we have an angle, like so, and we have the angle bisector. The angle bisector cuts this angle in half, so that angle is congruent to that angle. So we know we have the angle bisector. Well, here's our point on the angle bisector. It could be any point. What this theorem tells us is this point is the same distance from the sides of this angle. So I'm going to go towards the side of the angle and make a 90-degree angle. And this says that these two, those two are congruent. So anywhere on this angle bisector, if I go towards the sides of the angles, these two little pieces are congruent, yes. Well, these are on angles and these are on segments, so I thought it was okay. I can switch it. Let me go. No, yeah, I think I thought about it too. So let me do that and that. There we go. To make it 100% clear. So these two distances are the same. So if we wrote this in symbols, I'm going to call this point Q, R, and S. So I'm going to say if ray SP bisects angle QSR, and segment PQ is perpendicular to ray SQ, and ray P or segment PR is perpendicular to ray SR. So we're going straight towards it. Then PQ equals PR. We're bisecting the angle. We're going straight towards the sides of the angles. These two segments are congruent. And let's think really quickly before we write the converse. If we didn't know that these two segments were congruent, and we wanted to prove that these two triangles were congruent. Kind of the same thing. What do we know about segment SP between the two triangles? It's the same. It's congruent to itself. So if we wanted to show that triangles were congruent, we'd have a angle side triangle and an angle side triangle. So the triangle would be congruent by angle side, and these two segments are congruent by CP. So to prove that this is true is not particularly difficult. All right, questions on what this is telling us? Okay. Now let's write our converse. Converse, we're just switching the order. So we say if a point is equidistant from the sides of an angle, then it is on the angle bisector. So our picture here, we're going in reverse. So here we're starting off knowing that our point is halfway between the sides of the angle. So here's our point. And if we go straight towards the sides of the angle at a 90-degree angle, if those are congruent, then this point has to be on the angle bisector. So that point, if we drew the point through that, the ray through that point, we would know that that angle is congruent to that angle. So we're just saying this in the opposite direction. These two are the same, then this bisects the angle. So questions on what this theorem is telling us? Now let's think about this one as saying that ray, whatever is bisecting the angle, it has to be right in the middle. It has to be the same distance from either side. All right, let's do one last example, and then we will be done. So here's our picture for this one. And we know that these are congruent. So before we even write down the rest of the problem, what is this? What is this ray? What kind of special thing is it? It's the angle bisector, because these two are congruent, cutting this big angle in half. All right, so let's draw some more pieces here. And always on my drawings, make sure you go by what the problem tells you, not by what the problem looks like, what the picture looks like. And this problem says find OP. So we already decided that LO is an angle bisector. So what do we know about these two distances? They have to be the same. They're congruent. These segments are congruent. So we can say that 6x equals 3x plus 12. And now we're home free. We subtract 3x. 3x equals 12. Divide by 3. And x equals 4. And we're done. Did we finish the problem? No? The problem says find OP, not find x. So let's find OP. OP is 3x plus 12. 3 times 4 plus 12. 3 times 4 is 12, plus 12 is 24. OP equals 24. All right, questions on that example? Nothing really complicated that we did today. Just kind of the theorems have a lot of words in them. But the ideas are not particularly complicated. All right, so what I want to do, why don't we write down, before we stop, write down our homework. Well, should have some time to work on this afterwards. So page 296. There's that. You stop this.